Welcome back, everyone, to part 5 of our time series explainer. I am absolutely thrilled to have you here today because we're uncovering a massive milestone in the history of forecasting. Up until now, we've looked at different pieces of the predictive puzzle totally in isolation. But today, we're going to see what happens when the greatest statistical minds decided to put the whole shebang together.
Okay, let's dive into this, because this is the central mystery we are going to solve in this explainer. What exactly happens when a forecasting model doesn't just look at what happened in the past, but also rigorously analyzes how wrong its previous predictions actually were? It's a fascinating concept, and honestly, it completely revolutionized how we predict the future.
Chapter 1. Why choose one? Think back to the two highly distinct complementary forecasting philosophies we explored previously. We had two different camps of thought, each with its own mathematical superpower. On one side, we have auto regression, or AR. This approach assumes that today's value depends on yesterday's value. It learns directly from historical observations. Then, on the other side, we have the moving average model, or MA, which takes a completely different path. It forecasts using past forecast errors, or residuals. But taking a step back, you really have to ask yourself, if both approaches capture incredibly valuable information, why should we have to choose between them? The brilliant answer is we don't. Statisticians realized that by combining these two philosophies, they could create something far, far more powerful. This became known as the ARMA breakthrough, the autoregressive moving average model. It was literally the very first model to combine the memory of past data with the error correction of past mistakes into one single, elegant mathematical framework. It was a massive breakthrough for the field, and we're going to see exactly how these two seemingly different ideas work together. Chapter 2. The Best of Both Worlds. Before we look at any complex equations, I want to build your intuition on how this unification functions in practice. Imagine the physical pipeline of the ARMA model. It's basically a system where historical data and historical errors flow into two separate funnels. The autoregression funnel processes the actual numbers from the past, while the moving average funnel processes the mistakes we made when trying to predict those numbers. And this brilliantly illustrates how these two streams process their information simultaneously and then merge, generating one highly refined combined forecast right at the other end. By doing this, we get the absolute best of both worlds. The AR component provides long-term memory. It captures those underlying temporal relationships, like, how a stock price that's been rising for 3 days has momentum, or how today's temperature is heavily dependent on yesterday's. But the MA component, it acts as a shock absorber. Imagine a sudden, totally unexpected machine failure in a manufacturing plant that disrupts output for just one single day. The MA component looks at that sudden residual error and accounts for its fading impact, completely preventing the model from overreacting to a temporary anomaly. This brings us to the formal definition you'll see everywhere in classical forecasting: ARMA PQ. I know it looks a bit complex, but it's actually incredibly straightforward. The P simply dictates how many steps back we look in our autoregression pipeline. That's our memory. The Q dictates how many steps back we look in our moving average pipeline, our error correction. They just tell the engine how far back into the past it should reach to predict the future. Simple as that. Chapter 3. Inside ARMA. Now that we have our mental model locked in, it's time to look under the hood and gradually explore the mathematics of the ARMA engine itself. Let's start with this foundational quote from our source material. It states that the current value of the series is determined by the long-term average plus a random shock right now plus a weighted sum of past random shocks. In other words, today's prediction isn't some sort of magic. It's just a baseline that we constantly adjust based on recent trends and our previous forecasting mistakes. To make those adjustments, the engine relies on a few crucial gears. We have the autoregressive coefficients represented by the Greek letter phi, which decide how much weight to give our past observations. We have the moving average coefficients, represented by theta, deciding how much weight to give our past mistakes. We also have the residuals, which are the actual errors, and white noise, representing the purely random, unpredictable fluctuations in the system. The beautiful part is that the model learns all these parameters directly from the historical data. So the crucial point is this simplified equation. The predicted value, y at time t, equals a constant c, plus the autoregression terms, plus the moving average terms, plus the current error. AR and MA are working hand in hand simultaneously during every single prediction. This synergy is exactly why ARMA often produces significantly better forecasts than using either method completely on its own. Chapter 4. Engineering Applications. Let's ground this beautiful theory in absolute reality. How do engineers and data scientists actually use this engine out in the wild? Well, the sheer scale and utility of ARMA and classical industry systems is staggering. Because it's computationally efficient and incredibly robust, it became the foundational architecture for forecasting across massive sectors. We see it everywhere, predicting weekly retail demand for consumer goods, optimizing complex supply chain inventories, forecasting financial market returns, planning manufacturing output, anticipating call center volumes, and even predicting insurance claims. It is everywhere.
But deploying this in the real world requires a really delicate balancing act, specifically when choosing our P and Q parameters. If an engineer sets the order too low, the model becomes too simple. It misses the underlying context and cyclic patterns. But if they set the order too high, adding way too many lags, the model risks overfitting. It essentially just memorizes the historical noise, which completely ruins its ability to accurately forecast new, unseen data.
Now, what's really interesting is how engineers solve that balancing act. They don't just guess the values of P and Q. They use powerful computational tools like the autocorrelation function, or ACF. The ACF mathematically analyzes the time dependence in the data, measuring how strongly a series is correlated with its own past values. This allows engineers to run model diagnostics and estimate the perfect optimal parameters.
Chapter 5: The Biggest Limitation.
Despite its elegance and widespread adoption, the ARMA engine has a massive hidden vulnerability that we really need to talk about. That vulnerability is a hidden assumption called stationarity. For the ARMA math to actually work, it requires the fundamental rules of the environment to remain completely constant. It assumes that the statistical properties of the time series, specifically the mean and the variance, do not change over time. Basically, it needs a perfectly stable world. But let's think about the real world for a second. What happens when the data keeps trending upward? What happens when inflation keeps rising year after year? Or when a startup business just keeps growing exponentially? In the real world, things are rarely perfectly stable, are they? This introduces a concept known as non-stationarity. When the environment fundamentally shifts, when the mean drifts upward or the variance wildly expands, the ARMA model breaks down. Its memory of the past and its error corrections are no longer valid because the underlying rules of the game have totally changed. ARMA simply cannot handle a changing reality on its own. And that leaves us with a profound realization. Before we can accurately forecast the future using this incredible engine, sometimes we first need to mathematically transform the past. We literally have to alter history before feeding it into the ARMA pipeline. Let's move to and see how this builds our roadmap for the rest of our exploration. In our next explainer, we're going to dive deep into this hidden assumption of stationarity. We'll uncover why almost every classical forecasting model utterly depends on it and how data scientists wage war against shifting trends. Which leaves us with one final, fascinating question to ponder until next time. If the ARMA engine cannot handle real-world trends, what mathematical trick allows us to step in and literally flatten reality itself? Think about that, and I will see you in our next explainer.